Yes or no? Yes or no? अरे कुछ तो बताइए.
Yes, sir.
Right. So we were discussing about the induction motor drives, and this is the schematic, general schematic for induction motor drive, right? And of course, the schematic represent that the schematic represent the drive when we are having a DC power source, right? So when we will having a DC power source, but we want to make an induction motor drive, what we will use as a modulator, power modulator? What will we use? We will use a DC to AC converter, which is known as inverter, right? And it will depend upon whether it's a single phase inverter or a three phase inverter. It will depend upon the requirement of the induction motor, whether we are using a single phase or a three phase, right? So based upon that, we will be selecting the inverter that will be serving the as a power modulator for this drive, right? Of course, to make it a closed loop one, we'll measure the speed and will pass on the information to the control unit, where the decision will be taken to generate the optimal firing pulses for this inverter, so that we can have the desired output from this motor, right? So that by controlling the power flow from the source to the motor. Is this clear? Need
Yes, sir.
right? We should never forget that whatever drive we make it for a certain load requirements, right? So first we'll see the load requirements, and accordingly we'll design the our drive, right? So this is the basic schematic for an induction motor drive, and in this drive there are two main components. One is the induction motor and the other is the inverter. I guess you already have studied this inverter, right? The working of the inverters and the type of the inverters in the course of electronics. The functioning and the behavior of the induction motor you could have learned in the course of electrical machines, right? But still, because this is the key component of the induction motor drive, I guess I have told you about the working of this induction motor, and there were certainly the four questions which I tried to answer you and to make you understand. And first one was, why do we call it as induction motor, right? This was the first question. I guess now everybody in this class knows this fact, that why do we call it as induction motor? Any one of you? Why do we call it as induction motor? Why do we call these motors as induction motors? Huh? Any one of you? Just raise your hand. Sunil wants to tell it to the class. Hers and Astu and Sweta. Okay. Let us give a chance to Sweta first, right?
Sir, we call it induction motor as it works on the principle of induction. स्टेटर हमारा जो मैग्नेटिक फील्ड जनरेट करता है, इंडक्शन के थ्रू हमारा रोटर वर्क करता है.
Basically, right. Basically what she wants to say is your motor, this induction motor, is a singly excited machine, right? And singly excited means we only give the supply, we only connect the stator winding directly to the supply, right? Your rotor windings receives the energy from the stator winding by the means of induction, right? So that's why we call this motor as induction motor, because the rotor is receiving the power from the stator or the supply by the means of induction. Is this clear, bacho? I guess it's clear to the class. Yes. And now everybody can answer it, right? Now raise your hands who knows this fact, that why do we call it as induction motor? Why do we call it as induction motor? Raise your hands. Again, the same person is raising the hand. What happened to others? Kumar Aditya, will you be able to answer it, beta? Still not?
Yes, sir.
हाँ बताएं. Why
सर
do we
वही
call, right?
इंडक्शन मोटर में सर स्टेटर से इंडक्शन के थ्रू मतलब रोटर को वो मैग्नेटिक इंडक्शन होता है तो सर वो वर्क करता है. That's why we call it
right. Basically the power जो ट्रांसफर होती है रोटर सर्किट पे, it's by the means of induction from the stator, yes, right? From the stator the power is being transferred, because what we are doing, we are feeding the power to the stator. We are feeding the power to the stator by connecting it to the supply, but the rotor receives the energy from this stator by means of induction, right? there is no electrical connection between the stator and the rotor windings, right? So that's why we call it as induction motor. Hopefully now it's being very clear to other students as well. So can you raise your hands who have now cleared this fact that why do we call it as induction motor? Raise your hands directly, everybody, if you understand this. If you have understood the concept, please raise your hand. Uh, okay, so now still 6-7 people have raised their hands. Still, I guess there is doubt or they are not listening to me. Fine, you can put your hands down. Nothing can be done now. So these are the induction motors, right? And we call it as induction motor as the rotor receives the energy from the stator by the means of induction, right? One other question, although I already have answered it, why do we call it as singly excited? Because we only, what is the answer? Why do we call these machines as singly excited motors?
Sir, only stator winding is excited.
Very good. Because we only connect the stator winding directly to the supply. So we only give the excitation to the stator winding, right? The rotor receives the energy by the means of induction itself, right? The third one, answer key, why they are self-starting in nature? These motors are also self-starting. Self-starting means even if we take an induction motor, right? Three-phase induction we are talking about, right? We are talking about three-phase induction motor. So if we take a three-phase induction motor and we directly plug it on to the supply, it will start rotating, right? It will start rotating. It will not require any starter for that purpose. Okay. So they are self-starting in nature. So why they are self-starting in nature? It is because of the rotating magnetic field which your stator develops, right? So because when we supply three-phase, when we connect your three-phase winding of the stator to the three-phase supply, what happens? A rotating magnetic field is developed in the air gap, right? And because of that rotating air gap, your rotor starts rotating. So basically this motor is a self-starting motor, right? Because of that rotating magnetic field. Is this clear? Is this clear, Bacho?
Yes, sir.
So I guess these three questions are very clear to the class. Why do we call them as induction motors? Why do these are called as singly excited, and why they are self-starting in nature, right? So these are the three basic concepts. We already have discussed we can classify these motors based upon the AC supply they are using, they require for their operation. One is the single phase and other is the three phase, right? And if we talk about the three phase induction motor, they can be classified into the two categories. One is the squirrel cage type, the other is the wound rotor type, right? The difference between the two, if we see in the terms of working, if we see what will be the difference between the two, the squirrel cage, in the case of squirrel cage, they both are the kind of rotors, right? So it is on the basis of the type of rotor the induction motor have, right? So your three-phase induction motor may have a squirrel cage type rotor, or it may have a wound rotor type rotor. So based upon those, your motor will be classified. Okay. So what is the limitation of a squirrel cage type? Who will tell it to me? What is the limitation of a squirrel cage type? See, what happens in the squirrel cage motor is, in case of squirrel cage motor, your rotor conductors, they are short circuited by the end rings, right? They are short circuited by the end rings, like this one, right? So they are short circuited by the end rings. These are the rotor bars. They are short circuited by the end rings. Now, because they are short circuited by the end rings, what happens is they do not have an option, means they do not leave the option to vary the torque of the motor, right? As we can do in case of wound rotor. In case of wound rotor, your windings connections, they are being brought outer, they are brought out for the connection to the external circuit, right? And because of this external circuit, we can connect on the external resistance, and this resistance can be used to increase or decrease the torque depending upon our requirement, right? But because of this limitation that it does not have any, we require basically the arrangement to connect a stationary part to the rotating part. Your rotor is the rotating part of the machine, and this is the outer circuit which is being there in the outer environment. So what we know we require is this mechanism, which is called as slip ring and brush assembly, right? So we require this arrangement for connecting a circuit that is being static to a rotating circuit. Now, because of this presence, because of this mechanism, what happens? This makes this machine costlier and the and require the frequent maintenance, right? Whereas your squirrel cage type motor, whereas please mute your mic, please mute your mic.
ये जाता है, ये गेट खुल जाता है। नहीं, गेट तो खुल जाएगा, गेट खुल जाता है, कोई बात नहीं।
Please mute your mic. Okay. See, your squirrel cage motor, because the rotor windings are being short circuited by the end rings, what happens is they do not require the slip ring assembly. Because of this slip ring and brush assembly, they are maintenance free, they are cheaper, right? So your squirrel cage type motors are cheaper, rugged, right? Whereas your wound rotor types, they are expensive, right? Of course, they require frequent maintenance, of course, but they also provides you the provision to add on the external resistance, and because of which you can control your torque speed characteristic of the motor, right? Is this clear? Is this clear?
Yes, sir.
Right. Okay. So this already we have discussed. Why do we call it a singly excited machine, and how do this rotating magnetic field is developed? One more point: this rotating magnetic field, which is being developed by this three-phase machine, when we connect it to the three-phase supply, it rotates at a speed which is called as synchronous speed, right? So at which speed this rotating magnetic field rotates? This rotating magnetic field rotates at the synchronous speed, right? And the synchronous speed is being given by an expression ns is equals to 120 f by p, right? Where ns represents the synchronous speed, f represents the frequency of the supply. This is the supply, so this will have an associated frequency with it. The frequency of the supply, this f represents the frequency of the supply, whereas the p denotes the number of poles of the machine, right? So you can say that if we are feeding a motor that is having a 6 poles, and we feed it with the supply of 50 hertz, obviously the synchronous speed will be equal to how much? Everybody calculate, write it in the chat box. How much will be the synchronous speed for a motor which have a 6 poles and being fed it with the 50 hertz of supply? Write your answer in the chat box. I will take your attendance from there. Everybody write your answer. What will be the speed, synchronous speed of the machine if it is a 6-pole motor and having a when fitted with a 50 hertz of supply? What will the synchronous speed? I got an answer from still from the 7-8 peoples only, so I will be putting their attendance only, right? Everybody is answering to be 1000, but still some everybody hasn't put their answer. Everybody write your answer. Okay, fine. I will see and I will mark the attendance only for those who have answered the questions, right? Now what will happen? Suppose if this motor, the same motor which is of a 6-pole, right? If this motor which is of a 6-pole being fed with the 40 hertz of supply, what will be the synchronous speed? If we feed it with the 40 hertz, motor is same, but what we are doing, we are connecting it to the supply which is of a 40 hertz. Now what will happen? Whether the synchronous speed will increase or decrease? What will be the synchronous speed? Now write this in the chat box. Fine. So Shweta has, she is very promptly written the answer, and very good. Keep it up. Yes, the speed will get decreased as the frequency will get decreased, right? As the frequency of the supply will get decreased, the synchronous speed will get decreased, right? And there will be a different speed. You can see that if we are feeding a motor with the induction motor with a different frequency of supply, there will be a different synchronous speed. Of course, if your slip is being constant, right, then the rotor speed will also be varying with the frequency. So one of the fundamental parameter by which you can change the speed of your induction motor is the frequency. Now it's very clear to the class, I guess, right? The other is the pole. So by changing the pole also we can change the speed of the motor, right? Now suppose if we keep this to be 40, but now suppose we make these poles equals to 12, what will be the speed? I'm talking about that earlier when the motor was having 6 poles and being fed with the 40 hertz of supply, the synchronous speed was 800 rpm, right? It is 800 rpm. But when we make this motor to be a 12 poles, what will be the new speed? Any guess? No. Anybody written the answer? It is 1400 or 400, right? It's 400. So new speed will be 400. So by increasing the number of poles, we can decrease the synchronous speed again, right? Now there is a term which is called a slip, which I just have named upon, and I think already we have discussed about this slip. Slip is what? It's the relative difference between the rotor and the magnetic field by which it is rotating. We already have discussed that your rotating magnetic field, it rotates with the speed called as synchronous speed, right? So your rotor, it always tries to catch up that speed such that there will be no flux cutting action and such that there will not be any EMF induced on the rotor conductors, right? And because of no EMF there will not be any current, and because of absence of that current there will not be any torque, right? So to reduce that torque basically which is being acting on these conductors, because of this rotor is being rotating, right? Because of this rotor is forced to rotate, what happens is it's natural that your rotor starts rotating in the same direction in which your rotating magnetic field is rotating, right? Now although it tries its best to achieve the speed, but because the force or the power or the energy because of which it is rotating, it is only because of that relative difference. So it never being able to attain the synchronous speed, as if somehow it attains that speed, what happens is the relative speed between the rotor and the rotating magnetic field, it becomes 0, right? And once it becomes 0, you can see that it's a situation of a kind of magnetic locking, where your rotor is also being rotating with the synchronous speed and your magnetic field is also being rotating with the synchronous speed. So if we see the magnetic field from the point of view or by standing over the position of a rotor, right, it will look like a stationary. And same if we see it with the frame where your rotating magnetic field is being rotating, if we stand over there and we see the rotor positions, rotor conductors, we'll see that they are looking to be stationary to each other. Because of that, there will not be any flux cutting action, and if there will not be any flux cutting action happening with the rotor conductors, obviously there will not be any EMF induced on those conductors, right? When there will not be no EMF, obviously there will not be any current in the rotor conductors, and because in the absence of the rotor conductors there will not be torque developed in the rotor. And because in the absence of torque, what will happen? Your rotor will slowly slow down and may stop even if in the absence of any synchronous speed. Although there will be a rotating magnetic field until and unless we disconnect your stator winding from the supply, right? So what happens is your rotor, although will not be able to attain the speed equals to the synchronous speed, but it almost achieves that speed. So it runs just near to that synchronous speed, right? And that relative difference is called as slip. We call it as slip. Slip is nothing but it's the expression and mathematically we represent it by ns minus nr over ns, right? And you can see from here that this slip varies. If we take it from 0, means if suppose your motor is at a standstill, means if your rotor is at a stationary or a it is at a rest condition, right? So during the rest your rotor speed will be 0. So when rotor speed is 0, your slip becomes 1, right? So your rotor start, you can say that at starting your slip will be 1, but it will, as your speed will gradually increase, this slip is going to decrease, right? And certainly your motor will start rotating and it may go up to ns only, where if we take it to be a case, although it cannot be possible in case of induction motors, it will be a hypothetical case. But if we take this one, that suppose your rotor is rotating with the speed of ns, what happens with the slip is that your slip becomes 0, as nr has taken up a speed of ns, right, equals to ns. So ns minus ns becomes 0. So you can see that when your motor starts rotating from the speed 0 and certainly it rises up to a certain speed, then your slip basically decreases from 1 to 0, right? So as your motor speed goes up, your slip goes down from 1 to 0, right? It moves from 1 to 0. I guess it is clear to the class. Is it clear, bachcho? Is this clear?
Yes, sir.
Fine. Also, there is another fact that the frequency of the induced EMF, basically because of which the current flows in the rotor windings, it also being related with the slip, right? So if we say about the rotor side frequency, right, rotor side frequency, then this rotor side frequency f2 is basically equals to s times of f1, where f1 is the stator side frequency which corresponds to the supply frequency, right? So the frequency on the rotor side f2 is basically equals to s time of f1. So you have to keep it in your mind, and you can even learn it. Why do this is okay? So your f2, that is the rotor frequency, is equals to s times of f1, and you can see that if during the starting the value of slip will be how much? At the time of starting the value of slip will be
1.
how much it will be? अरे स्टार्टिंग में स्लिप कितनी होगी?
Sir, 1 होगी.
1 होगी.
1.
Right. Slip, the value of slip will be 1, as the during starting nr will be 0, so obviously slip will be 1. When slip will be 1, you can see that rotor frequency will be equals to the supply frequency. So जब रोटर रुका होगा उस समय पे जो इंड्यूस होगी जो भी करंट या ईएमएफ इंड्यूस होगा उसकी जो फ्रीक्वेंसी होगी वो इक्वल होगी सप्लाई फ्रीक्वेंसी के. लेकिन जैसे जैसे रोटर घूमने लगेगा वैसे वैसे क्या होगा कि स्लिप की वैल्यू 1 से कम होगी. 1 से कम होने का मतलब ये है कि रोटर साइड जो फ्रीक्वेंसी है वो जो पहले थी वो उससे कुछ कम होने लगेगी, राइट? इज दिस क्लियर बच्चों? इज दिस क्लियर?
Yes, sir.
Yes, sir.
Obviously when your rotor is rotating with the full speed, that means your rotor has achieved a speed somewhat lesser than the synchronous speed, right? So at that time slip value will be very, very close to 0, right? And if it is very, very close to 0, you can see that the frequency of that rotor side will be very, very less, right? So you can understand that during the normal rotation or the normal speed, the frequency on the rotor side will be very, very less, right? And this is the reason why generally when we talk about the losses in case of rotor circuits, right, we do not consider the rotor core losses. We consider them to be the negligible because they are frequency dependent losses, right? In the machines we have two kind of losses. One are the copper loss and other are the core loss, right? So in the induction motor, we'll have a core loss and copper loss on both the circuits, right? Whether it's a stator or a rotor, we'll have a core and copper losses, right? Is this clear, bacho?
Yes, sir.
We will have a means these core and copper losses will be there in both the circuits, whether it's a stator or rotor. But in case of rotor, when it is being rotating at a normal speed or a full speed, right, the rotor core losses, they will be negligible. Why? Because during that condition, the frequency will be very low on the rotor circuit, right? And these core loss are basically the frequency dependent losses, right? So because of that, the core losses will be negligible, can be considered as negligible, right? So if we talk about the total losses in the machine, there will be stator core loss, there will be stator copper loss, and there will be rotor copper loss. We can neglect the rotor core loss. Always, because these are the rotating machines, we can add up on the friction and windage losses, right? So total losses in the induction motor, they will be the stator core loss, stator copper loss, rotor copper loss, plus friction and windage loss. Is this clear? Is this clear, bacho?
Yes, sir.
Right. Now we already even have discussed about the per phase equivalent circuit, right? So to analyze the machine, people have proposed the equivalent circuits, right? Although we are considering the three-phase motor, but we will be studying the behavior of the induction machine by the help of this per phase equivalent circuit. It's a equivalent circuit for a per phase, means for a single phase, right? For a one phase, right? So you all guys, I guess you already have studied this in your last year course, right? Electrical machines. And in this course, you can see that we have two circuits, one that is being on the stator, other that is being on the rotor, right? But over here, what you can see is they have merged the two, right? We are having a rotor circuit parameters as well as stator circuit parameters on both on the single side, right? So this is basically a equivalent circuit where rotor circuit parameters are being referred to the stator side, right? Basically, these are the rotor circuit parameters and these are being referred to the stator side, right? Xm represent the mutual induction between the two, okay? It is for that purpose, and the magnetic field that is being required, it is basically representing that case, okay? So if we see this circuit, what does it basically represent? It's representing the equivalent per phase equivalent circuit referred to stator side, right? So I guess it is very clear why do we have associated the slip term with the rotor resistance, not with the reactance. Although we know that with the slip only, or with the slip, as with the slip, your frequency is being associated, right? If we talk about the F2, it is equals to S time of F1. So your F2 is being associated with the slip, right? And we know that only your X2, that is XR over here, it depends upon F2. Yes or no? Because XR is what? It will be 2 pi F2 L2, where F2 will be the rotor side frequency. Yes or no? Yes or no?
Yes,
So
sir.
basically, we know that if we talk about the rotor circuit, right? If we talk about the rotor circuit, I guess I've already make you understand why do we add on this this slip with the resistance rather than to be the reactance. Have I make you understood? No? Yes or no? Yes or no? Bolo jaldi.
Yes, sir.
Right. I guess I have made you understand why do we add this this value of slip with the resistance in place of reactance. Although we have understood and we know this fact that your rotor resistance or resistance does not varies with the frequency, right? Only it is the reactance that is being vary with the frequency. right? Because reactance, if it in general, this reactance X is what? It is equals to 2 pi Fl. Yes or no? So basically your reactance, if we talk about rotor side reactance, let it be X2, then it will be equals to 2 pi F2L2. Yes or no? But what will be the value of reactance on the rotor side? It will depends upon the frequency on that rotor side, and that will be equal to 2 pi F2L2, right? We know that this F2 depends upon the slip value, and we can write this as SF1L2, right? So your X2 basically equals to S time of 2 pi F1L2, right? We know that F2 is equals to F1 during starting. So this is the reactance during starting, right? So your X2 is basically S time of reactance during starting. This will be the X2 at any slip S. I guess it is very clear to the class, right? Okay. So basically we know that reactance is equals to S time of X2, right? S time of X2, whereas R2 will be independent of this S. But yes, the EMF that is being induced, on the rotor side, it also depends upon the S. It is also being S is also being associated with this. So to instead of being having the effect of this S over 2, what is being used or what is being recommended is to take on this effect to the single variable for the analysis purpose, right? And as you can see over here, what will be the value of I2 for this case? I2 will be equals to S time of E2 divided by under root of or you can write it as R2 plus J times of SX2. This will be the value of slip. This will be the value of current, rotor current. Yes or no? Yes or no?
Yes, sir.
So if this will be the value of rotor current, what we can do is, can we take this value of S common so that we can take on the effect from the 2 and can pass it on to the 1? The answer could be yes, that yes, we can write this expression, this one expression as E2 R2 by S plus J times of X2. Can we write it like this way?
Yes, sir.
Right? So what this represents is the circuit where we can write like this one. This represents the circuit where we have R2 by S, one X2 and an EMF E2. Then also the current that is being passed on will be the same that as this one, right? So this circuit is being used for simplification purpose, right? So you can see that in case of these circuits, your slip is being associated with the resistance, not with the reactance, although actually it should be with the reactance. I guess it is very clear to the class now. Is this clear बच्चों? अरे बता दो जल्दी.
Yes, sir. Clear.
Yes, sir.
ठीक है. Now to further simplify this case, what is being proposed is to take on this shunt branch to the leftmost side, right? And this will be the circuit then. And if we see over here, we can easily calculate the value of the current that will be flowing in the rotor side, right? That will be the rotor equivalent current, right? And how much it will be if V is the applied voltage. If we divide this V by the impedance of this branch, then we'll have the value of I2, right? Then we'll have the value of I2 that will be equals to V divided by RS plus RR dash by S plus J times of XS plus XR dash. So I guess this we have done in our last class, that your value of rotor equivalent current, right? This is IR dash, that will be equals to V divided by the impedance of this branch, this one, right? This is the branch. So if we take on the reactance of this and divide by the voltage which we have applied, right? So we'll have the value of the current. Now what will be the power that is being transferred to this rotor circuit? This is the rotor equivalent circuit, right? So the power that is being transferred is called as air gap power through, because it is being transferred, the power is being transferred through the air gap from the stator, right? We call it as air gap power. How much it is? It will be equals to the 3, because it's a 3-phase motor. But if we talk about the single, this per phase equivalent circuit, it will be equals to the current that is being flowing and being passed on, or and being absorbed by this rotor resistor, right? So this will be IR dash square, because this is the current that is being flowing in this circuit, right, into the R2 by S. So this is the air gap power, means this is the total power that is being received by the rotor circuit from the stator, right? And if we multiply by 3, this will be the total power by the 3-phase motor which is being received from the stator from the stator, right? Now this is the total power. What happens is, as we already have discussed, that there will not be the much more core losses, but yes, copper losses will be there, as they are independent to the frequency, right? They are independent to the frequency. Because the frequency is very, very low, the core losses will be negligible. Is this fine? Core losses in the rotor circuit will be negligible, but still the copper losses will be the dominant losses, and they had to be included, right, to check on that what will be the final output power that will be converted into the mechanical power, right? So the copper losses that will be occurring in the rotor circuit will be 3 times of IR dash square into RR. That will be the copper losses. And if we subtract the 2, means if we subtract these copper losses from the total power that is being received by the rotor, we can get the power that is being converted into the mechanical power by the rotor circuit, right? So obviously it will be Pg minus Pcu. So if we subtract this, we will get the mechanical power expression for the mechanical power, that is equals to 3 times of, if we subtract this one from this one, right? No, if we subtract this one from this one, right, subtracting the 2. So it will be 3 times IR square into RR dash 1 minus S over S. This will be the mechanical power, right? Now this mechanical power, we know that this mechanical power is the product of torque into speed. It's a multiplication of the 2 power, right? 2 component, one is the torque and other is the angular speed. From here we can derive the expression for the torque as T will be equals to Pm by omega, right? This Pm is nothing but it is equals to 1 minus S of Pg. If we see these relations, these 3 relations, we can get that Pm is nothing but it is 1 minus S of Pg, whereas omega m, that is nothing but it is equals to 1 minus S of omega S, where omega S is the synchronous angular speed and it is the angular mechanical speed, right? So we can see that your torque can be written as Pg by omega S. We already have derived the expression for the Pg, which represent the air gap power, right? Air gap power is 3 times of IR dash square into RR dash by S, right? And if we divide this Pg by omega S, we'll have the torque. Now what is being done over here to get the final expression in terms of voltage, right? It is in terms of current. To have it in terms of voltage, the IR dash square, the value of this IR dash has been put as in terms of voltage, right? We already have calculated this IR dash in terms of voltage. So we put this value in the expression, in this expression, and finally we get this one, which says that the torque will be equals to 3 times of V square over the impedance of the circuit into RR dash by S, right? And if we plot this expression with respect to the slip, we'll get a characteristic like this one. We'll get a characteristic like this one. And this is called as torque speed characteristic, right? We call it as torque speed characteristic. Okay. And in this characteristic, the torque which we get during the starting, we call it as starting torque. And you can see in this characteristic that this torque will keep on increasing up to a certain point, and after that it will start decreasing, right? Of course, when your speed will be equals to ns, the torque will be equals to 0. It should be 0, right? It should be 0. So the torque where it is being maximum, we call it as maximum torque. Obviously it corresponds to the certain speed, right? Always you can see that in this in the complete range of speed, you are not going to have the same torque from this machine, right? You will get a maximum torque at a certain speed only, and that certain speed will correspond to a certain slip also, right? And that slip at which we get the maximum torque, we call it as maximum slip, right? We call it as the slip at which maximum torque is occurring. So we generally denote it by SM. This is not the maximum slip, this is the slip at which we are getting the maximum torque. Is this clear, bachcho? I guess it is clear. I guess it is clear, right? And if we differentiate this torque, this expression with respect to slip, we'll get that value of slip at which the torque will be maximum, right? And this is the SM. SM means the slip at which maximum torque will be occurring. You can see that the expression which you will get is having the expression which says that that slip is directly proportional to the rotor resistance value, right? So what does it indicate? It indicates that if we increase the rotor resistance, the torque at the slip at which torque will be maximum, it is going to increase, right? If we increase, I'm repeating my statement, if we are increasing the rotor resistance, right? If we are increasing the rotor resistance, then what will happen? The slip at which maximum torque will occur, it is going to increase, right? So if we increase the resistance from R1 to R2, if we increase the resistance from R1 to R2, so then this characteristic will going to shift to this side. So this will be the new slip, as your slip will going to increase with the increase in rotor resistance. Is this clear, bachcho?
Yes, sir.
Now what will be the net effect of this? You can see that with the same motor, if we increase the rotor resistance, the starting torque can be increased. First thing, this torque at which it will be maximum, the speed at which the torque imparted by this motor will be maximum, this can also be varied, right? So we can increase the starting torque even by increasing the rotor resistance. Okay, is this clear? But what will happen to the maximum torque? Is this fine? It is very now clear to the class that yes, there will be a shift in the slip at which this maximum torque will occur, right? So with the increase in rotor resistance, the slip at which maximum torque occurs, it is going to increase, right? But what happens to the maximum torque? Does it also increases with the rotor resistance value, or it decreases? So answer is, when we put this value as of SM, which we have derived in the expression of the torque, what happens is we get this expression, and this says that there will not be any effect of the rotor resistance on the maximum torque capability of that motor, right? So it says that even if we increase the rotor resistance, the maximum torque of the motor is not going to increase or decrease, right? That's why you can see that this maximum torque, whatever was the earlier was the maximum torque capability of this machine, it will also remain same for the new resistance, which is now the higher resistance than the previous one. Is this clear, बच्चों? अरे बोलो हाँ ना तो बोल दो, खत्म करें क्लास।